So yesterday was a lot of blackboard work, working out the semantic EFT, and I wanted to wrap this up today. So this was meant to be the ending of yesterday's lecture with an example that I kind of skipped over, putting it all together. So I've showed this slide before, but now we've put a lot more meat behind with the semantic EFT lecture, explaining where this analysis comes from. My notes have more information about these approaches. I didn't get through them either, but you can get through the notes. And in fact, how this works by the example of the energy-momentum relation and the quark propagator. We discussed some of these examples, and we sketched how relativistic heavy quarks work with something that is an improved Wilson action. And more of the story is in the notes, including a little bit more, though it gets sketchy, about lattice HQET and NRQCD. Okay, so now that we know how to deal with heavy quark systems in lattice QCD, leaning heavily on effective field theories, which of course makes a lot of sense because we have this additional scale that gets introduced. So you do want to treat this with an EFT, and in fact, EFTs are the backbone of how lattice QCD is an ab initio method, and hence also how to properly treat heavy quarks. So now that we live in an era where we have available to us gauge field ensembles with lattice spacings that are not always larger than the Compton wavelength of the B quark. We don't have ensembles where the lattice spacing is much, much smaller than the Compton wavelength of the B quark, where we can resolve it in a similar way as we can resolve the charm quark or the light quark degrees of freedom, of course. But we can certainly push to where we can use some simulations at fine lattice spacings where the B quark discretization errors are not completely uncontrolled. So this means that one can do a series of calculations. We do many lattice spacings anyway, and compute quantities as a function of the heavy quark mass, and then interpolate or extrapolate as the case may be. And this really only works if one has an improved light quark action. So now we use the same action for light quarks as for heavy quarks. For heavy quarks as for light quarks. What this does is it provides a much simpler renormalization scheme because this action is the same. You can now use ward identities, and mass dependence is just the source of discretization error, so one can use mass-independent schemes. And so this is the way in which the errors that are hard to reduce in these EFT approaches that are really hard to reduce below a 1% level. One has to work much harder, and we all know that perturbation theory in lattice QCD is much more annoying than in the continuum. Going beyond, especially with all of these scales in the system, going significantly beyond one loop could be done, but it is difficult to really push this reliably to the precision that we want to be at. Okay, so however, even when we have a highly improved light quark action and we're pushing calculations where the B quark mass, or the heavy quark mass in lattice units is less than 1, but still not small compared to 1, there's still large discretization errors in this approach. And the analysis that we've done here then also suggests how to control these better. And this is what I wanted to talk about. Let me talk about that here. So we've looked at the energy momentum relation of the Wilson action. Here is a highly improved light quark action. This is the it's even called that. Highly improved staggered quark action. I didn't make up this name. These people did in HBQCD. This is the tree-level version of this action. The version that includes the gauge fields, it's harder to write down because there's lots of smearing involved. And the smearing is needed in order to control one of the dominant light quark sources of discretization effects, which come from the fact that there are still unphysical degrees of freedom. They're called tastes with staggered quarks. And there are taste breaking interactions that are discretization effects, and they provide the dominant discretization effects that can often be described by the splittings in the pion system. So there is some Chi-PT control, EFT control over those as well, and I'll come back to that when I talk about G-2. Okay, so this action has a higher order derivative term in it in order to include order A squared improvement. And this term here is called the Nike term because here the improvement condition is worked out by including the mass dependence. And so the improvement condition is that when you work out the way we did before, but this is going to be a little bit more annoying, the energy momentum relation, then the rest mass is again m1, and m2 is defined in the same way. And if we consider that the improvement condition then says that m1 and m2 for any given value of m0 should be equal to 1. Of course, when m0 is 0, that is automatically the case. And so this gives a relationship then between m1 and m0. Well, this yields this expression over here. You can see how annoying the analytic expressions are, but they can be worked out, of course. And then the improvement condition gives a value for this coefficient. So if one adds this coefficient with this to this operator, then for any value, for any given value of m, the energy momentum relation is automatically improved to being equal to E squared equals P squared plus M squared, with M1 and M2 being equal, and of course then there are higher order discretization terms. So this removes terms that are of order AM squared as well as other leading A squared terms. This, in this sense, then this is a highly improved action that is for light quarks as well as for heavy quarks. Now, the same way that we worked out the fact that when you have when you add mass to the quark propagator, that the normalization of the fields changes, that also happens for the His quarks, and you get these expressions. So you should also adjust the normalizations of the heavy quark fields in the same way. And then you should also, instead of using M0 as the to define the physical mass, you should again use M1 to define the physical mass. So with these modifications, then the remaining discretization errors in this for heavy His quarks are indeed very, very small. Basically, the discretization errors are not that different from light quarks. So now I want to remind you of what we discussed for rare leptonic decay, how the B meson decay constant features in here, and how the standard model prediction has a small uncertainty because we've computed this decay constant with such small errors. And so now here's a picture of the underlying simulation. This is a paper that's aging very well. It came out in 2017 at the end of the year. So here's a picture of the Milk collaborations, gauge field ensembles that use that HISC action with a Nike term with the up, down, strange, and charm quarks in them. So these are just displaying two of the many parameters that are in the action, the C quark pion mass and the lattice spacing. This is plotted here quadratically, to emphasize that the discretization errors vanish at least quadratically. The size of these disks, so these disks indicate a gauge field ensemble at these parameters. The size of the disk is proportional to how many configurations there are. And then you can see that the Milk collaboration has collected gauge field ensembles at quite a few different values of the lattice spacing down to 0.04 Fermi, all at physical pion mass, and then a whole bunch of other ensembles at heavier pion masses. And then there's also changes in the different volumes and different strange quark masses and so on. It's a large library of gauge field ensembles that have been used by quite a few collaborations. So with this, one has pretty good control over discretization effects. And with the lattice spacing down to 0.04 Fermi, one can also resolve the B quark mass, as is shown here. So these are the valence parameters, the valence quark mass, heavy quark mass parameters on all of these ensembles. And you can see here, this line indicates the physical B quark mass. And you can see that on the finest ensembles, we have, in this simulation, we get values that get very, very close to the physical B quark mass. On the finest ensemble, which is not at physical mass, the physical B quark mass is entirely covered. So you have, from the coarsest lattice spacings to the finest lattice spacings, you can map out an increasing number of heavy quark masses, and so then compute the decay constants and masses and et cetera as a function of heavy quark masses, as a function of lattice spacing. And here are the results. So this is a subset of the data projected to, only looking at the physical mass data that are used. So what is plotted here is something that's proportional to the decay constant versus heavy quark mass. Over here is charm. So these are then, you can read off the values of the D meson decay constants, and over here is B. And what the colored lines are the fits to the lattice data, and then the cyan blue bands are the continuum extrapolated decay constants as a, of course, still as a function of the heavy, in this case, heavy meson mass in some scale setting, using some funny scale setting quantity that was nice to compute here. So what you can see here that is interesting to note is that the fit that describes the data that then is taken to the continuum limit, the data points that are not included in the fit, those are data points that are shown here in open symbols, are still described by the fit. So this tells us This is one indication that we have a really good description of the discretization effects here. And the purple curve hugs, gets close, hugs the cyan curve, because that is the one at the finest lattice spacing shown here. And then as you go to coarser lattice spacings, you can sort of see how it peels off, as you would expect. And over here is shown is an illustration of the size of the discretization effects. So showing at various values of fixed heavy mass the dependence on AM squared. And what you see here is, at the heaviest masses we don't have that many data, but we can see that really the discretization effects are small. They are surprisingly small until you remember that the leading AM squared effects are removed. So this really shows you the power of doing this energy momentum investigation and removing those effects. And this can also be done a posteriori, I claim, at least, shifting to adjusting the bare mass to adjusting the mass so that the rest mass corresponds to the physical mass and the field normalization. I think this analysis can be used, for example, also for domain wall fermion simulations that are using a similar approach, but don't quite have the small lattice spacings. So that's
Good question. So the plot on the right-hand side, that is the result of a global fit to all of the data, and then for the individual quark masses, you reconstruct those curves. Is that
yes.
So the x-axis is sort of the lattice spacing measured in units of the heavy quark mass?
Yes.
Yes. Okay.
Yes, it's basically slicing the data in different ways, but here it's looking at it at a fixed physical heavy meson and physical units.
So it means that the larger the lattice, the coarser the lattice and the larger the heavy quark mass, the fewer points you have because you're sort of squeezed into that corner on the previous plot.
Right, exactly. So that's why here there's fewer, and why, at the smallest physical mass and physical units, there is a lot more. Okay. And again, here's the same symbol. The open symbol here is not included in the fit. Okay. So with this improvement, then the same principles for why this works as well as it did for F-pi and for the K-on form factor, the same principles apply here. And this is really the engine behind the sub-percent level calculations of the heavy meson decay constants. Okay. So unless there are questions, I would now move on. Well, I should stop. Please, are there any questions about yesterday's lecture on semantic improvement, or on, I should cover this, my kid is mortified when she realizes that her 5-year-old self is shown in mouse costume when she was a mouse in the Nutcracker. Okay. Questions?
So the quantity phi.
Yes.
Which quantity is it exactly?
So this is the decay constant times the square root of the meson mass. So this is the thing that has a finite limit in the heavy quark limit. Yes.
Okay.
Thank you. Sorry, I should have defined that. And this FP for S is similar to F pi, but it is at a quarter of these are evaluated at a quarter of the strange mass. So this is a fictitious scale that we use to have a common scale setting. so that everything is expressed in a common scale, and then this is related to the pion decay constant for scale setting. So this is similar to using gradient flow scale setting or relative scale setting from R1 or something like that. Okay.
What are the dashed lines?
The dashed lines here indicate the cutoff in AM. So we use a cutoff of AM 0.8. So data points beyond on the right side of the dashed line are heavier than AM 0.8, and so they're not included. But we can still see how well they are described by the fit function. So the colored lines are the fit functions at finite lattice spacing. So that was the point I was making. And then the solid lines correspond to the B and D meson values. Okay. So let me now move on to mu on G minus 2. Okay, so here is the outline. So we'll start with a quick introduction to the anomalous magnetic moment, just starting from the beginning. Hopefully this is well familiar. So the magnetic moment arises from the combination of electric charge and spin of a fundamental particle. In the Dirac theory, the G factor, this is where theory comes in, is equal to 2. And then you can compute quantum corrections from loop diagrams, loop Feynman diagrams, and they will modify this vertex and hence will modify the G factor. And the first calculation was done by Julian Schwinger in the late 1940s, and that was a very important result. So this diagram is called the Schwinger diagram, and he computed that G minus 2 is alpha over 2 pi. That's inscribed in his tombstone. It was such an important result. It went along with the first measurements of the spin magnetic moment of the electron, and there was big excitement when the experimentalists found that the electron's spin magnetic moment compared to the angular magnetic moment was yielding a G factor that was a little bit greater than 2 after Dirac had predicted it to be 2. So that was a puzzle until Schwinger and others, there were quite a few people who were working on this. I think he was the one that got the result out first, showed that you have these quantum corrections, QED corrections, will explain the experimental results. So this was part of the establishing of quantum electrodynamics as the correct theory of electrons and other leptons and photons, and understanding how to deal with loop calculations and quantum corrections in this quantum field theory. So accepting quantum field theory as the correct framework to describe the standard model. That was the beginnings of it, and that's why it's inscribed in his tombstone. So in principle, we will have contributions from all sectors and all standard model particles if we are challenged to compute this to high enough precision to confront with experiment. And the interesting quantity is then the deviation from 2 that is here defined in terms of this in terms of the form factor. And the anomalous magnetic moment is the way that it is defined, arises due to loop corrections if if there were no loop corrections, then A would be equal to 0. So this is a rare quantity similar to the rare decays that we have already discussed. So as a rare quantity, as a small correction, it is also sensitive to potentially to new particles. And there has been this experimental effort that started at CERN and at Brookhaven, where there was a 3 to 4 sigma tension, apparently with standard model predictions. And I will tell you about the most recent development. So this has been a very exciting and continues to be a very exciting topic to study. Okay, but here we focus on the theory, and we need to compute the contributions from all the sectors. So we have QED, electroweak, and hadronic. And here are the results shown. This is from the latest white paper. So this is the Schwinger term, and then QED has been computed through 5 loops. And that's why it's known with 2 parts per billion. Compare that to the experimental precision, which was what? Was less than 130 parts per billion. So QED is good, right? Then electroweak has been computed through 2 loops, and that gives us something like 3 parts per billion. Why is the electroweak correction so much smaller than the QED? It also is 1 loop. Yeah?
I mean, the mass of the Z boson is very large in comparison to
Right.
the rest of the system.
Right. So electroweak corrections are suppressed by lepton over heavy boson mass squared. So that gives you that large suppression, and so this is the natural size. Very good, and that's why 2 loops is certainly more than enough. And now hadronic contributions, quarks contribute starting at 2 loop order. So also in the electroweak corrections at 2 loops, you will have quark loops. But because the electroweak correction itself is so small, it's not a huge source of uncertainty, but it actually is one of the biggest sources of uncertainty in this 3 parts per billion. At 2 loops, then we can have the photon split into a quark-antiquark pair, which creates a hadronic bubble. And you can have other diagrams with vacuum polarization. This is what this is, hadronic vacuum polarization bubbles. So this has been, you can compute this through what here we call next to leading order, so including alpha cubed and alpha 4 terms. And this is the second largest contribution. QED completely dominates everything, and it is the by far dominant source of error. And then another pesky hadronic contribution is this called hadronic light by light. So if you take away the muon line, then you have 2 photons to 2 photons, and that's why this is called hadronic light by light scattering. And this is smaller because it starts at alpha cubed and has this very interesting structure. And then you want to add next to leading order corrections, so alpha to the 4 terms as well. So this is smaller. This is closer to the size of the electroweak contribution. Again, because it is hadronic, the error is much larger, but this is commensurate with the experimental precision. And that is by itself, and that is already quite an achievement that gets overshadowed by all the drama around the hadronic vacuum polarization. And I'll mention this very briefly. There should be another lecture on hadronic light by light that Harvey should give, or Hartmut should give, but I won't really talk about hadronic light by light very much. Okay, so that is the situation, and I'll come back to what I mean by white paper. It's always nice to illustrate this graphically with a pie chart. Actually, pie chart is not quite appropriate. If you look at the contribution, it's all QED, and you only see this because I cheated. The hadronic vacuum polarization is a teeny tiny sliver here. I enhanced it. And you don't see any red here or orange because these are completely irrelevant. So the error now is really all about hadronic vacuum polarization.
What is 0.9% mean? Yeah.
So that's the precision.
Okay.
So 61 divided by 7045. So this is a sub% precision result. But sub% precision, very good. So sub% precision is not enough. This is a factor of 4 times larger than the experimental precision. So, we need to reduce this to not just the percent level, but something that is sub 0.5%. So we really need to get to below 5 per mil. So now stop talking about percent and talk about per mil.
So the uncertainty of high light by light is larger than.
Yes. So very good questions. I was going to make these points later, but we may as well make them here. The precision with which you need to know the contribution, of course, also depends on the size of the contribution. And we'll see this when we talk about the different pieces to the hadronic vacuum polarization itself, right? Because the size of this is so small, knowing it with 10% precision, roughly speaking, is giving us an uncertainty contribution that is already smaller than the experimental uncertainty. Refining this by a factor of 2, which is completely realistic, will then, reduce the overall uncertainty contribution even more. And so basically, the story for light by light is that, we are already at the precision level that is needed, and reducing this further to where the hadronic light by light contribution is a not concerning source of uncertainty anymore is very straightforward, I would say. And I'll show you where this comes from a little bit later. So what this means is that really, as a community, our effort our focus needs to be on the hadronic vacuum polarization. While we don't want to forget light by light, we certainly want to improve that as well. Okay. Other questions? So then a reminder, or maybe an introduction. The hadronic vacuum polarization, the way that when people were talking about, and even when we discussed this in white paper 20, about the 4 sigma discrepancy with or tension with the experimental measurements of G-2, those statements were based on, that I should have removed. Those statements were based on data-driven evaluations of the hadronic vacuum polarization, which is using dispersion theory. And I have a little bit more of an introduction to that in the appendix. I'm going to skip over that. Dispersion theory is using the principles that allow us to formulate the QFTs in the first place. So we're using unitarity, analyticity, etc., to relate the hadronic vacuum polarization, the hadronic vacuum polarization function to a cross-section E plus E minus goes to hadrons that can be measured and has been measured. And so the problem of computing the hadronic vacuum polarization in this framework is rephrased as a problem of measuring the hadronic cross-sections and the precision by which the data-driven method evaluates the hadronic vacuum polarization contribution is driven by the experimental precision. Unfortunately, in the last couple years, the cross-section measurements, in particular in the dominant pi-pi channel, have diverged rather than converged. So there are now very large discrepancies between different measurements that prevent us from using this method as a precision HVP to determine HVP with precision. And I'll show you some results for that. But this is an ongoing effort, so new measurements are coming along. But that is why white paper 25 was based on the first consolidated lattice HVP average, which is, of course, you know all of this. So this is just to contrast the in lattice QCD. Now we evaluate the hadronic vacuum polarization. Instead of integrating over center of mass energy, the cross-section here, we're integrating over Euclidean time. This is also a weighted integral with a kernel that comes from the loop diagram, same as this kernel. But now we're integrating the 2-point functions, correlation functions of the electromagnetic vector current in the background of the gauge fields. And so these are now lattice data, and how well we compute this depends on how well we compute the lattice correlation functions. So that's the analogy here, and that's what we'll focus on. I wanted to say a few words about the muon G-2 theory initiative. Harvey mentioned that my role in here. And you will recognize, some other names here. Hartmut has been a member of the steering committee for a number of years now, and there's more minds presence with Achim Denik, who's an experimentalist here. And you might recognize some of the other names. So this brings together the community. The steering committee is also representative of the community, and we have all of these workshops. The last one was in Japan. That set the stage for the white paper that we put out, and we're going to meet in a couple months in Orsay to talk about the next steps for the next white paper. So the goal is to pool all our knowledge together and have consolidated theoretical understanding of this important quantity from all points of view. So here's a timeline. The theory initiative started in 2017, and we had our white paper, first white paper in 2020, and the second white paper came out. We knew when the Fermilab experiment was releasing their final announcement, and we squeaked in our white paper a week before with lots of drama and sleepless nights. But we got it in, so we have a clean theoretical prediction prior to the reveal of the blinded experimental measurement. And I'll show you the results of that now. So in 2021, when the Fermilab experiment released their first measurement of their run 1 data, the white paper had come out in 2020, and there was this very intriguing 4 sigma tension, where the white paper 20 evaluation was based on data-driven evaluation of HVP. And now in 2025, you can see how the green has exploded, kind of like confetti. So the experimental situation is shown here, the data-driven. There's a new result by CMD3 that disagrees with everybody, including their previous iteration of that experiment. And I have some explanation of the acronyms also in the appendix. So this is why we're not using that. And we have our first consolidated lattice HVP average. That is what the white paper 25 prediction is based on. and the central value differences are now less than 1 sigma, as you can see. But I want to emphasize that really this is a snapshot in time. There's puzzles here. There's puzzles between the comparison between data-driven and lattice. They should agree. If they don't agree, we need to understand why. So this is not done, and whether or not there is some new physics in here in this situation, we don't know yet. So it's still a story that is evolving. And here is a little bit more detail. Again, looking from the HVP point of view, this is a situation in 2021 where we were using data-driven evaluations. And here's the white paper 20 result and band and the results that went in. And you could see that already by the time of white paper 20, there were lattice results. The errors were large. And we had a lattice average that had a large enough error that it covered both the data-driven and the experimental measurement. So basically, it didn't weigh in whether or not the standard model agrees with the G-2 experiments. And so it wasn't part of the average. And so there is some consistency between the picture here with large errors and the picture here with small errors. What you also see there are now 3 groups that have on their own computed almost all contributions to the hadronic vacuum polarization, and those are shown here. And they are very compatible with our consolidated average, which is mainly based on slicing and dicing the contributions and adding them up, giving us more information, and I'll talk about that in a minute. And here you can see a more detailed situation breakdown of the experimental situation. This is mostly all of this variation comes from different ways of understanding the pi-pi cross-section measurements. Okay. So now that we have that, let's go one interlude quickly, because I might not have time to talk about hadronic light by light very much at all. I wanted to show you the final result. So there are 3 lattice groups that have provided results that are these are the lattice calculations. You can see that they are very well consistent with each other and allow then a nice average. There is now a new dispersive result for light by light that's much, much harder, and there's a long story there as well that I'm not going into, but there is a consolidated average from using a dispersive method and some theory inputs and some experimental inputs. And what is nice for light by light is that the dispersive data-driven average for light by light and the lattice average for light by light, they are quite well compatible with one another. So we have an overall consolidated average that is given here, compared to what we had in white paper 20, which was mostly driven by a not quite complete data-driven average and one lattice calculation with large errors. There is a 1 sigma shift, roughly speaking, in the central value, but good compatibility with what we already had in white paper 20, with an error that is reduced by a factor of 2 to the 10% level. Yes?
In your previous slide, what is the main difference between, because you have average 1, average 2, blah, blah, blah. What's the main
I'll get to that.
Okay.
Thank you. Yes, I will. This will be easier to explain when I talk about how we took the average, and you'll see that explicitly. But yes, good question. I will talk about that. Okay. So let's go back and flesh out what I said before in a little bit more detail. So we start from an expression like this for the hadronic vacuum polarization, which is, this two-loop integral where the vacuum polarization function is itself a loop contribution, is written here, and this is a function of q squared after you consider Lorentz invariance. And then this is the kernel that comes from the loop integral. And then in lattice QCD, of course, we compute correlation functions of Euclidean time. You guys know that. So we compute a correlation function of two electromagnetic currents. And we have to compute the contributions from all flavors in here. And the way that usually this correlation function is phrased is at zero momentum. So the sum over spatial x projects out zero momentum. And then we can take the Fourier transform of this, the subtracted Fourier transform shown here. That can be plugged into this integral. The integral can be rearranged. So we can rewrite the hadronic vacuum polarization in terms of directly of the correlation function with an integration kernel that is basically given by this expression over here. And this was worked out really nicely in a seminal paper by Bernecker and Meyer, and the Meyer is Harvey Meyer sitting here. And so this is basically the workhorse for all the communities, the international communities, work on hadronic vacuum polarization. And as Harvey likes to point out, of course, we can consider other ways. We can consider computing this correlation function not just as a function of Euclidean time, but as a function of Euclidean distance, and work out those integrals that gives us a different way of looking at the problem. This is called the coordinate space, CCS. Covariant coordinate space method, so you can look that up. I'm not going to be talking about that because I'm focusing on the results. So this gives us a different way of then also, the systematic errors will contribute in different ways in this formulation. So one can certainly expand the way that we do these calculations in other ways, and that's a good thing to do to make sure that we're not overlooking something. But all the calculations that I show are based on this. Okay. Now, I also wanted to quickly mention that the higher order kernels, so the next to leading and next to next leading order kernels, have been worked out also for Euclidean momenta, and also at least partially in the time momentum representation. So that means that we can take our lattice correlation functions and also directly compute the next to leading and next to leading order. Here are shown results that are based on the Minkowski space kernels and the data-driven method. But we have everything, all the tools needed to get lattice QCD evaluations of the next to leading order and next to leading order contributions as well, which are of course much smaller, but in order to, at the precision level, they are relevant. Particularly the next to leading order one is definitely relevant. Okay. So as I mentioned before, we need to compute the contributions from all flavors. And, we don't, of course, in lattice QCD, look at the hadronic channels. We set the flavors because lattice QCD is QCD. And there's a hierarchy of contributions here. Because the hadronic vacuum polarization, the diagram here, the muon, the external muon, means that this loop integral is dominated by low q squared. So this is this diagram is actually quite quite infrared dominated. That's why the hadronic vacuum polarization contribution is in principle a non-perturbative quantity. Perturbative QCD does not, is negligibly, contributes negligibly here. And that then also makes sense that in the data-driven method, it's the pi-pi channel, the lowest hadronic channel that dominates. It's about 75%. And for the in the lattice calculation, the light quark contributions dominate. They weigh in at close to 90% of the total. So whatever our precision target is, the light quark contribution, light quark connected contribution, is going to have to be computed at the precision target. It will drive the overall precision. And then we have subdominant heavy quark contributions. As you go heavier, less and less dominant. In particular, the B quark contribution can be computed perturbatively, but there's also some non-perturbative calculations of it. Strange and charm, we really do need lattice QCD for. We have disconnected contributions. This is disconnected in our language. Of course, there is the quark-gluon background, so there are gluons that connect these. These kinds of diagrams are notoriously difficult and noisy. So the computational methods we use for the disconnected versus connected contributions are different. So it makes sense to compute them separately. And then, of course, we need to include isospin breaking corrections. In particular, the more difficult corrections are the QED corrections. The strong isospin breaking is not so hard to include.
So the disconnected contribution is negative or positive? So if the disconnected contribution is negative,
The sign. So these are not signs here, right? Yes, the disconnected contribution is negative typically. So these don't add up to, these seem to add up to more than 100% because there's also signs here. So this is just the size, how much it weighs in, and since you asked that question before. This also gives us a guidance for how hard do we need to work in order to, what precision is needed. The light quark connected, we need to compute that at the target precision. So whatever per mil precision we need, 5 per mil or so on. However, the disconnected contribution, computing it at 10% or 5% is completely sufficient. Same with QED. However, whatever precision, we still have to have full quantification of all systematics. There is no forgiveness here, because it is, right, we're making contact with the real world. We really want to know whether or not, to decide whether or not the standard model is broken, we really have to be really careful. Okay. So then the challenges are well known. So as I said, we need this at the less than 5 per mil precision. I think getting to 5 per mil in the next couple of years is realistic. So one of the stumbling blocks is that the correlation function that we're computing is a correlation function of the electromagnetic current. Electromagnetic current is a vector, right? So we have a vector current correlation function. And it is well known that vector current correlation functions have a signal over noise problem. And so we have an exponentially growing noise for large T. And this is troublesome when we are when we're computing spectral quantities, masses, matrix elements, etc. We fit the correlation functions, so having growing noise is troublesome, but we can usually get enough information at smaller lattice spacings to get the desired spectral information. But here, we need to integrate the correlation function over all Euclidean times. So noise reduction strategies are very important here. And this is where a lot of work has gone in order to get to the results that I will show you. We also have sizable finite volume effects. Again, this hadronic vacuum polarization is a multi-scale quantity by itself. It is very sensitive to scale setting uncertainties. This was pointed out by the Mainz group, Hartmut and others, quite a long time ago. And of course, we need to control discretization effects in this of this multi-scale quantity, and some of the ways in which we're dicing the calculation helps with that. Okay, so there's lots of challenges. And then something that evolved almost by the hour or by the day as we were working on white paper 25 is understanding the results and the scheme dependence of the various results. So if we want to not just average the total HVP calculation, of the various groups, but if we want to actually look at the pieces and compare different contributions computed by different groups, then we need to understand whether or not the groups are using the same separation scheme. So let me talk about that actually in the next slide. So here's a slide that explains why, despite the fact that this is the dimensionless quantity, it is sensitive to scale setting. So it's basically because it depends on the muon mass. And the muon mass, of course, is known in physical units. And so we use our lattice scale to convert. And so as was worked out in this paper, it turns out that whatever the scale setting uncertainty is, the relative scale setting uncertainty, that is enhanced by close to a factor of 2 in the hadronic vacuum polarization. So again, it is via the dependence on the muon mass that's basically driving it. So if you have a 5 per mil precision scale setting calculation, well, that's already 1% error just from scale setting. So this is important then to really also improve the scale setting to high precision. So this is important, of course, for the overall precision program for computing anything, but it is also crucial for hadronic vacuum polarization. And that brings us to what scale setting quantities are used. There's kind of 2 that are commonly used. Ultimately, even if one uses a fictitious relative scale setting like gradient flow or the potential scales are 1 or whatever, ultimately the scale is set with a physical quantity because it's only by comparison with experiment that we know what the physical dimensions are of our lattice. And the physical quantities that are used are either the pion decay constant or the omega baryon mass. One doesn't use a light meson mass because those are used to set the masses. So that would be a nice quantity to use as one of the masses in the light meson sector because you can compute it very precisely, and there's also information about QED corrections, and there's no radiation and so on. But those are needed for the masses to set the masses, and hence the decay constants have been used traditionally by many groups. The omega baryon mass is an interesting one to use for scale setting. So it's easier to compute because it's all strange quarks compared to nucleon. And it's large. QED corrections to it are small. It is stable under the strong interactions. So it has those good properties, but it's a baryon. Baryons are always more annoying. But as a baryon goes, it's much easier to compute the omega baryon mass than the nucleon mass. And the systematics are easier to control, again, because it's all strange quarks. So that's why this is an interesting quantity and why many groups are starting to switch to the omega baryon mass. So one disadvantage, F pi can be computed very precisely. I showed you the precision and the flag average, and so can Fk. However, the way that those quantities are then used in scale setting is we don't experimentally measure the decay constants. What we experimentally measure are leptonic decay rates, right? And the leptonic decay rates, of course, also depend on CKM matrix elements. So if we compute F pi and want to use it to set the scale, then what we need to compare to is the experimentally measured decay rate with VUS or VUD already taken from somewhere else, like nuclear beta decay. So if you use F pi or you use Fk, then you bring in uncertainties from CKM matrix element determinations. So your F pi scale setting depends on nuclear beta decay, and that now feeds into the hadronic vacuum polarization calculation. And similarly with Fk, it depends on VUS, and I showed you that there are some puzzles also around the VUS VUD determinations. That if you care about also possibly contamination from these sources, then you might turn to the omega baryon mass. So that's one reason why the omega baryon mass is quite attractive, because it does not require any additional external inputs. I think ultimately it's a good idea to have various scales and go back and forth between them to understand if there's any issues with scale setting as well.
Why did you say that? Because the omega baryon mass is a baryon made up only of strange quarks. You can control the systematics better rather than with a...
So finite volume is, again, because strange quarks are heavier, finite volume effects. You do have to, of course, address them, quantify them, but they're going to be milder than for nucleon. So everything is a little bit easier because the omega baryon consists of strange quarks. The computations are simpler, the inversions are faster, finite volume is simpler, and so discretization errors, of course, are going to be the same. I mean, the strange quark does not give rise to larger discretization errors generically than other light quark quantities. So it's not worse. Here the omega baryon is not worse, like a charm quantity might be worse. So that's my reasoning.
Why is finite volume simpler?
Not simpler, it's just, strange quark systems are smaller. Because they're heavier. So this, of course, what matters in the end is, this here is still what the measure is still e to the minus m pi L. So roughly speaking, broadly speaking, it's the same problem for nucleons and for omega baryons. But if you are computing, if you're computing this in different finite volumes, you're going to have a little bit of an easier time here. I mean, I'm expecting that the finite volume dependence actually computed by computing this at different finite volumes is not going to be worse, at least, than for the nucleons. Okay. So let's talk about a separation prescription. So I've already mentioned this a couple times, right? The real world is not just QCD, but QED is always there. So when we use meson masses to set the quark masses and hadronic quantity to set the scale, those quantities carry charge, and they are experiencing both QCD and QED interactions. So really, we must do a QCD plus QED calculation. And if we're focusing on only QCD, then we must understand how QED effects are separated out. And this is where we need a separation prescription. If all you show are results that are coming from QED plus QCD, including all QED effects, then separation scheme description is not relevant. But if we want to compare flavor-specific quantities with one another, then having a common prescription where everybody uses the same definition of what is the pion mass in pure QCD or in isosymmetric QCD, what is the kaon mass, what is the d sub s meson mass that determines the charm mass, which is not written here but should be on here, and what value are we using for scale setting in order to define the isosymmetric QCD point or the pure QCD point. So pure QCD means this includes strong isospin breaking. That separation prescription then also defines the QED contributions. So if this is common, then we can directly compare different lattice results for flavor-specific quantities. This is something that really came together really only in the last month or so of putting together the white paper, how we can relate all the different results to a common scheme. For some results, this is still a source. We added uncertainties in order to account for some shifting in the scheme. I believe that the next round, all the groups will have more control over their separation scheme and will be able to provide more information so that translations to different schemes, where you might change the mass or something, will be easier. But doing this and understanding this and coming to an agreement as to what scheme and also what scale we're using was very important. This is not, the final result. This is what we used for white paper 25. We might come to a different scheme for the next white paper if that's more convenient. So it's really a matter of convenience. What is the thing that we define that we can all compute and that we can all compare with one another? As long as the calculation is then done and all the pieces are added up in one consistent scheme, the end result is scheme independent, as always. Okay. You can, all the results I show are shown in the white paper 25 scheme in the end. So let me say a few more words about finite volume effects. I think this is a story that all of you know. For hadronic vacuum polarization, it is advisable, and I think all the groups are doing this now, to have a direct finite volume study and not just rely on EFTs, because finite volume corrections turn out to be quite sizable. So on the typical ensembles with the volumes, 6 Fermi-ish, 5 to 6 Fermi boxes, the finite volume corrections are 3%. That's much larger than our precision goal is. So that means that finite volume extrapolations need to be controlled, well controlled. And so there are large volume studies by a number of groups, and they're increasing. I don't remember if you don't have a large volume study yet, but
well, we compare different volumes,
right.
but not at the scale of, like, I don't know, 10 Fermi.
10 Fermi, right. Yeah.
It's currently not. So.
Yeah. Yeah, so we are working on that. That's coming for our group pretty soon, and it just adds then to the available information, because the volume study is really less dependent on the discretization effects. So understanding volume dependence in one calculation gives information for other calculations as well, I claim. Okay, so there is been quite a bit of work on developing and understanding EFT approaches to these finite volume corrections, and you can see very brief descriptions of these here, and basically looking at all of these, and if you have a large volume study, looking how the volume dependence agrees with these approaches is a good thing, and then using the variation, for example, to also understand the underlying systematics is a good thing. For staggered fermions, there is further modification because, as I mentioned, there are taste-breaking interactions that result in different pions that have different unphysical flavors that are called tastes, having different masses. So those then have to be included in the chiral perturbation theory and in the finite volume EFT as well to make sense of those data.
May I ask the difference of next leading order chiral perturbation theory with the chiral perturbation theory plus the goal? In next leading order, the goal comes into the next level.
Yes. So, however, in chiral perturbation theory, the effects of the rho are described by an LEC, a low energy constant. The rho is not dynamic. And this is why there's the word model here. So phenomenologically, of course, at the scales at which we are computing the hadronic vacuum polarization, the dynamics of the rho is important. But this is not an EFT anymore. This is now a model where you add a rho as a dynamical degree of freedom that couples to the photons and couples to the pions, and you can use the rho pi coupling phenomenologically to add that. So this is a phenomenological description or a model, but it starts from chi-pt. So comparing this to this, then seeing how well they agree or disagree, gives you an idea as to how important yet higher order, chi-pt effects would be in the n² LO. There's also, it is also very, very clear that next to leading order chi-pt is not enough, right? It ignores the rho, and the rho is important here. And that's why there's these other descriptions too that via the pion form factor, for example, also directly know about the rho and provide a different. So there's some modeling here in the parametrization dependence, and you can also remove that eventually with enough lattice data and do this all very directly. So the modeling is not so important, but this is also a nice way that includes the actual physics without too much model dependence, I would say. So all of these then, there's the parametrization dependence here and some dependence on what you use here. There's the limitations of chiral perturbation theory. There's the fact that this is a model. there's also limitations in this relativistic pion EFT that was developed by Hansen and Patella, which again is mostly about pions, and again it depends on what you put in for the form factors here. So all of these have different weaknesses, and seeing how they all compare, especially if you have a large volume study and then do the remaining extrapolation. So this adds to the knowledge. Okay. So here's an example for those of you who are not so familiar with chiral perturbation theory of, I've only written this out for the next to leading order expressions, but there's also expressions at next to leading order. Obviously, they would be even more annoying to write down on a slide, but the principle is shown here. The finite volume corrections come from doing the chi-pt in infinite volume and in finite volume, and then looking at the difference. So you compute the hadronic vacuum polarization in chi-pt, and then taking the finite to infinite volume difference. And you can do this by either computing pi of q squared, or by computing correlation functions in a space-time formulation of chi-pt, and then plugging it in. And here's an explicit expression, and the archive link is here that gives you these explicit expressions, so you can play with that if you're inclined to see how this works. Okay. There are, as I said, a number of finite volume studies. A really nice one is by the BMW collaboration. They looked at an 11 Fermi box going from a 6 Fermi box to an 11 Fermi box. So where the remaining infinite volume extrapolation is now very small. And this is one way in their strategy of quantifying, of getting to sub% precision. And with a data-driven analysis, one can refine the remaining extrapolations even more. That was a recent result by them, based on the same results. I think I'm going to pretty much skip this because I don't have much to say about QED. But when you add QED, things become much more complicated because you have to treat a massless photon in finite volume. And one way to avoid that is by don't do QED in a finite volume. And this framework has been developed for light by the Mainz group and also by RBC, and is also being developed for QED corrections for hadronic vacuum polarization. If you do QED in finite volume, then you have to deal with power law finite volume effects. And there's a very nice workshop that happened last year where there's a lot of information on QED in finite volume and how to deal with isospin breaking corrections. That the link is there. Okay, so I mentioned that noise reduction strategies are very important. So using an improved statistical estimator is very important, and all the results that I show, BMW, RBC, Mainz, also results by Aubin et al., and now our results rely on this method. So, of course, the quark inversion is inverting a large, humongous matrix that has many eigenmodes. The noise in the long distance tail is driven by the lowest eigenmodes, and if we can compute those lowest eigenmodes exactly and hence use the exact reconstruction of the lowest 1,000, 2,000, 10,000 eigenmodes, that provides a very big improvement in the statistical precision as is shown here. So this is an essential workhorse for all HVP calculations these days. It doesn't it doesn't remove the signal over noise growth, but it moderates it. So we still need additional noise reduction strategies at the analysis level, employing known bounds, for example, to reduce the reduce the statistical errors, or computing additional correlation functions. So the noise is also driven by the fact that the vector meson correlation function couples to multi-pion states at large Euclidean times, which are not well resolved by the point-like correlation functions, by the point-like operators, and by computing them, by computing additional correlation functions explicitly and using them to reconstruct the tail of the correlation function, you can get a big noise reduction. And this is also something that many of the groups are doing, including the Mainz group. Here's a beautiful plot from the Mainz paper showing the reconstruction of the correlation function with at large T, and how that also is an important part of the noise reduction strategy of the Mainz group. And this was a thesis of my student, Sean Lehert. This is the first lattice QCD calculation with staggered multi-pion operators. So everything is harder with staggered. The thing that's easy with staggered is generating gauge field ensembles, is doing quark inversions. Staggered quarks are computationally very efficient. But then the fact that there are these additional tastes make the analysis harder. And in this case, if we want to use the same strategy as Mainz and RBC, we have to deal with the fact that we have a whole bunch of taste pion states that we have to take into account. And this has been done at a coarse lattice spacing, and you can see the gain in statistics here. Now, this can also be used, all of these data can be used to understand the row scattering parameters using the Lucia formulation. And extending this for staggered fermions is also something I'm working on with other people. So that would be another very interesting way that could also feed back into a refined understanding of finite volume corrections. Okay. And now we need to talk about another dicing of the calculation. This was proposed by the RBC collaboration. They looked at windows in Euclidean time because they were interested in pursuing a hybrid calculation, where noticing that when we compute the correlation functions at large time, you have all this noise. At small times, you have large discretization effects. But at these intermediate time distances, the statistics is great. We can get really small errors very quickly. And we expect this region, some people call it the Goldilocks region, to be relatively less affected by finite volume effects, relatively less affected by discretization effects compared to short distance for discretization and long distance for finite volume. So that was the proposal by RBC. The hybrid method doesn't work anymore. That hybrid method doesn't work anymore because lattice and data-driven don't agree in this region anymore. In fact, they disagree in this intermediate region the most now. But this is now an essential tool in which we slice and dice our calculation and break it up into smaller pieces and study the systematic errors in these different distance regions by looking at the three different windows: the short distance, the intermediate distance, and the long distance. And clearly, the long distance window is where the bulk of the signal is, right? So this comprises something like 60% of the total HVP. This comprises something like 30%, and this is less than 10%, the short distance. So the short distance is the smallest, It is the one that is most sensitive to discretization errors. The intermediate distance is intermediate in size. It's about a third, roughly. And it is relatively insensitive, and I'll show you results for that. And then the long distance is the largest, and it is the hardest, and also the most exciting in terms of having new results and having consolidation. Okay. So it was in the vein of, in the process of doing these HVP calculations, a paper came out in 2022 that was pointing to log-enhanced discretization effects in the short distance region. And this is a series of papers. Nikolai has been working out the anomalous dimensions of bilinear operators in a variety of different discretizations, most recently also for staggered fermions, to basically check to see if the picture that I drew you of the discussion that I gave yesterday in semantic EFT gets destroyed or gets modified. If you have large negative anomalous dimensions, then the picture that I gave with just having power suppressed discretization effects gets upended. And it turns out that they haven't really seen signs of this yet. However, at very short distances, in very short distance region, there will be not alpha S enhanced, but basically tree level log enhanced discretization effects that they worked out. And the first group who took them into account was the ETM collaboration. So here they show very nicely how you get a different continuum limit when you don't include them to when you include them. The RBC collaboration, the references are missing. I'll add them before I upload. So there should be references here. The RBC collaboration here shows a result where they subtract the perturbative QCD calculation as a function of an intermediate time, and you can see that as you add more and more perturbative QCD, you still get very good stability. So the shortest distances are computed perturbatively, and then you can increase how much perturbative QCD you have versus how much non-perturbative, and you can see that the result is nicely stable. So this tells us that, so this is a very good test of the method. So they didn't really do any corrections in their continuum extrapolations. They just didn't use the smallest distances. BMW came out with a result in 24 as well, where they included the log-enhanced discretization effects and removed them at tree level. And so you can see the differences between the corrected and uncorrected in red versus blue and green versus orange. And then there's two versions of the kernel that also differ in their discretization effects, all giving consistent continuum extrapolation. And we did something similar. We looked at, we have two different currents. They have different levels of log enhancement. In fact, log enhancement is absent in the local staggered vector current correlation function. We show that in the paper. And we allow for log-enhanced terms for the one-link current. And again, you see good consistency in all the continuum extrapolations. And here we compare our calculation to perturbative QCD and see how well it agrees and how stable it is. So basically, the message is that this was very important to realize. Including it gives completely consistent results now. So I think discretization effects in the short distance window with these methods are now well under control. In particular, comparing with perturbative QCD is a good way to check as well. So there's more about continuum extrapolations that I wanted to discuss. For staggered fermions, again, taste-breaking effects are a dominant source of discretization effect. Taste breakings in the pion spectrum can be treated using chiral perturbation theory or other EFTs. So you can use these EFTs to correct for them before taking the continuum extrapolation. And this is what the BMW group did in their 2020 paper. And here for the intermediate window quantity, they show continuum extrapolations with and without first correcting for taste-breaking effects. The no improvement is not correcting. The with improvement is correcting. And you get, a spread, but they use that spread for their calculation. However, when they do the same thing for the full integrand, they claim they cannot take a continuum extrapolation. So these green points are without adding first corrections due to taste splittings. Okay? It doesn't converge to the same place as when they add corrections. And this is really troublesome, at least to me. I would like to see whether this is resolved with their finest lattice spacing data, but in their latest paper, they don't show this because they don't really show continuum extrapolations of the long distance or full integrand quantities that they compute. However, we have our own staggered formulation. We use different staggered fermions. And here you can see that if we correct or not, we get the same continuum limit. So this is an essential test of our calculation that including taste-breaking corrections and then extrapolating, or extrapolating without taste-breaking corrections, that we get the same answer in the continuum limit. And then we also have two different currents, and everything converges to the same answer. The spread is included in the systematic error. So this is what it should look like. It's troublesome to me that it doesn't look like that for BMW.
In the second plot, what is the difference between the red and blue and gray? And what is
So the magenta is a one-link current. So it's
in the middle plot.
this one?
Yes. The difference between the red and blue.
Okay, so these are different ways in which they added taste-breaking corrections. What they do is that this is the chiral model that I described before. And what they do is they add taste-breaking corrections starting, as a function of Euclidean time. They start them here at 0.4 Fermi. That's the red points. They start them. The blue points are, when they add them, only at Euclidean times that start at 1.3 Fermi. And the gray is, okay, it says it here. It's a different variation where they use the chiral model in this time region between 0.4 and 1.3 Fermi, and then use next to leading order chi-pt, taste-breaking. So these are different ways in which they do the taste-breaking corrections. They all give the same continuum limit, and that spread is included.
But they don't do the extrapolation for the gray? They only do it for the red and blue?
Yeah, I think that's technical.
That might be, I think there's some versions where they include it. This might have been, it might be that they just show that it has a consistent but not included in their spread. I mean, it doesn't look that different, right? So it's just to use a different EFT, to use a true EFT chi-pt where it is valid, where it is applicable versus not. Okay. Oh my goodness. I do want to answer that question, so let me get to that, and I'm sorry for running a little bit over time. So these are the most recent results that you can see. Okay, I should have put this over here. So in October, RBC put their result for the long distance contribution, light quark connected long distance contribution. In November, the Mainz group released their result, and we were the latecomers in December, a Christmas present. We released our results, so this is now the full integrand. And here you can see the comparison in a common scheme, in the white paper 25 scheme. So there are some tensions, and those tensions are included in the average. However, this is also good compatibility, I would say. Obviously, we want to reduce the errors and we want to understand these tensions, and there are things to understand about the scale and scheme dependence, and I think we'll have some interesting discussions about that in a couple months. But this is really the centerpiece for the consolidated average. Without this, we would have not been able to do what we did. So now we have results, a compilation of results. This is now for the light quark connected, short distance, intermediate distance, many different results, and long distance, the 3 results I described, and then a variety of older and newer results for the full integrand. And then these can be, so here are the relative size of the contributions. And then you can rinse and repeat this. For example, for the intermediate distance window, light, strange, charm, and disconnected, and add them all up for each window. And once you have all the isospin symmetric contributions, you can add the isospin breaking contributions in the intermediate window and get the total. And rinse and repeat. So for the short distance, for the intermediate distance, for the long distance, so we can add things up this way, and then add them up this way, or we can add them up this way, get for each flavor the full, and then rinse and repeat this for the other flavors. And so this is how we obtain different consolidated averages. And so the first 3 here are different ways of slicing and dicing. The slicing and dicing is, I think, a really great way in which we can see how compatible everything is and then take the variations into account. And this also maximizes the input because different groups have computed different pieces and they're all included because we're adding the pieces up in different ways. So everybody's results weighs in on this. These 2 are based on complete calculations, and that's shown here. And here's the full averages in comparison. I'm going to skip to this. I think I've talked enough. The slides are online. There's lots of slides also in the appendix that have more details for some of the things. You guys asked too many questions, and I wanted to get to the end of this. I'm sorry for going over time. I hope that it was somewhat entertaining. This is an exciting topic, at least in my opinion. Thanks, guys.
Thank you very much for this very clear presentation. It's a lot of material that you managed very well.
Thank you.
Really beautifully.
Thank you.
So, are there any further questions? Yes.
So I think that many of the calculations are blinded data from blinded data, but since now several groups are in agreement with each other and in agreement with the experiment, do you think that blinding is still something we should do in the future?
Yes, absolutely. I think that, and at least our group is, is working on reblinding. So you can do this in different ways. For example, if you add another lattice spacing, what you can do is, do the analysis at that one lattice spacing, and add additive offsets or add a slope, so that that you know about, and then play with that and unblind, make a prediction for what the previous extrapolation says about the data point at that lattice spacing. Do your blind analysis and then check that. So there's various ways in which one can re-blind the existing analysis. One has to do this carefully. I think it is very important because, especially with so much there, confirmation bias is a danger. And I can tell you from my own personal experience, and I think this is true for all of us who've done this, especially for this high stakes one, if you're blind, the only thing that you worry about is how well do I understand all the errors. You don't look at how well you compare with anybody else. So you're more paranoid, and paranoia is a good thing. So you want to stay paranoid without going over the edge, of course, right? But it changes how the entire group approaches this. And, we have built a culture in our group, I think all the other groups have done this too, where you basically don't look at anything before it's blinded. Any time a collaborator shows me a result, wait, is this blinded? I don't want to see it unless it is blinded. And so we never look at anything like that. Of course, you can take away the numbers on the y-axis too, with scripting. So there's various ways in which you can do this. But you want to avoid knowing, remember at that data point was at that value. So the blinding has to be so that you can't do that. Yeah.
Yeah.
In the tail contributions, you mentioned something about the error. The correlation matrices, how big contribute to these errors in these tail contributions? The correlation matrices?
Okay, so the correlations between time slices. So of course, the correlations are important. It turns out that the statistical correlations between different regions in time are not very large. So if you're looking at correlations between, statistical correlations between short distance and intermediate distance and long distance observables, those turn out to be not so large. Of course, you integrate the correlated data over certain regions in time. You can compute the correlations, and when we add up, the different pieces, we want to make sure that we compute the statistical and systematic correlations. So that's that's an important effort. And as I said, correlations between different flavor contributions computed on the same ensembles, correlations between different like short distance, intermediate distance, and long distance observables computed on the same ensembles are not zero, but they tend to be quite small. Yeah. Yes.
So, is it possible to extract the pipeline channel from the lattice calculations, because there is a line over 10 over 9 factor to isolate the difficulty and the connective contribution from the pipeline channel. So if the 10 over 9 factor can be verified using the lattice calculation.
So what do you mean by pi channel? Do you mean
Isospin 1?
isospin 1? So just pi scattering and the isospin 1 channel?
Yeah, because we
versus isospin 0. Testing the 10 over 9 factor.
Yeah.
I mean, certainly, I'm not sure how. You can certainly compute I equals 1 and I equals 0 and include correlations. I'm not sure if you can get to a precision where you can meaningfully test the 10 over 9.
Well, some point in our 2017 paper, we pointed out that the disconnected, of course, could be tested, the asymptotic behavior of the disconnected, because that, well, depending how you define the ratio, that would sort of converge to -1/10,
Yeah.
for instance. That has been done a long time ago, but maybe not with the precision that we can reach nowadays.
Yeah.
But I think in general, if you're interested in making contact with a data-driven approach, then by construction, the lattice approach does not distinguish between different hadronic channels.
Oh yeah.
So it's always the inclusive contribution that you get. You can do the exact flavor separation in the lattice approach, but you cannot verify individual hadronic channels. They're not sensitive to individual hadronic.
So I understood his question to be doing the Lucia calculation, the pi scattering. This is what you meant, right? The pi scattering calculation, and the isospin equals 1, isospin equals 0. You have to do that with physical pion masses and the continuum limit, including isospin breaking corrections. And so this is where I'm not sure that.
Because a lot of finite order corrections methods are based on the pi channel. So
Yes.
So the correction is not enough to the total contributions to the leading order HVP.
The dominant volume effect comes from the
Yeah.
pi.
Yes.
And the corrections only works for the pi channel, or
I mean, the pi channel is the dominant
I
correction. In the EFTs, of course, they lean on, the pi channel as well. I'm not sure what you mean.
But I think we should probably
Yeah, okay.
leave this for the coffee
Yeah.
break, which is already important. So
Yeah,
Sorry?
Exactly. Yeah, so